Okay, so we're going to do, here's this. So since I can't really write in here, this will be interesting, but we'll do it. Sorry, my computer's glitching. My whole screen just went black. Okay, let's go. That's not the right thing. Okay, so we'll fill in this little table. So we're going to complete the chart with positive, negative, spontaneous, non-spontaneous, endothermic, exothermic, released and absorbed where necessary. And so we're going to do that. So with this first one, we're going to put in, so just so like you guys remember, like delta H here. Let me do that. I think it will. Yeah, so this is entropy if you don't remember. This is entropy, which is heat. That looks weird, but it's there. And see that? There's that. And then this is enthalpy. Oh wait, no, I wrote them backwards. This one is in enthalpy and the other one's entropy. Enthalpy. And this one's entropy. Okay. And so if, say, we have positive enthalpy, negative, well, that's not negative, negative entropy, and make them big, not that big. Never mind, just leave them small. And we have positive of both of these. So with that, do you think that would be spontaneous or not spontaneous? So this one will be non-spontaneous. And since we can look at this, and because because you have to, it's adding heat to the system, that means it's going to be endothermic. And that means it absorbs heat. So now we're going to take and we're going to flip all of them backwards. So if this H is negative, S is positive, and negative TAS is negative, or T delta S, sorry, is negative, and delta G is negative, then we will be doing it. So with that in mind, all of these others are going to be exactly opposite as well. So we're going to have, this is spontaneous. This would be exothermic. It's going to release heat. So what do you think happens if we have negative H, negative S, and this is positive, but we don't even know what this is? So just like we can look at the delta H, and just by looking at delta H here, we automatically know if it's going to be endothermic or exothermic, because this tells you right here, because the delta H is negative, that means that heat was released. And so it releases, that's not what we'll do. And so that makes it exothermic. What is delta G? That is a great question. Delta G is Gibbs free energy. I believe, and let me see. Pull up this PowerPoint. Have that up in another tab. Or another window, I guess. I think I believe he explained that in there. That probably is a better explanation than I have on hand here. I don't think I included that. Yeah, Gibbs free energy. That's what delta G is. And what's that? So back here. And then this one is going to be at if it's at a low temperature, then it's going to be spontaneous. I'm just going to write S because that's kind of a long thing. And if it's at a high temperature, then it's going to be not spontaneous, non-spontaneous. So if we have this as positive, and this is positive, I don't know why there's glowing in weird places. This is negative. And once more, we don't know what this is. What do you think the spontaneity is going to be? So at a low temp, do you think it's going to be spontaneous or not spontaneous? Whoa. At a high temp, what do you think of? So what do you think for the low temp? Spontaneous or not spontaneous? Just put a guess out there. Spontaneous. It'd be non-spontaneous. So you can kind of like get that a little bit because if you look at this and then you look at this, they're completely backwards. So everything here is probably also going to be completely backwards, and it is. So this one is not spontaneous. And then for the high temp, because this one's more backwards as well, spontaneous. Okay, so is that going to be endo or exothermic? It's going to be endothermic. Which means it does wet to heat. I have random things capitalized and not capitalized. So they're going to absorb or release it. It's going to absorb it. And we get that from like our enthalpy is literally what I'm looking at to determine that. So if you notice, if it's positive, so it's like you have this system, and if it's positive, that means it's adding energy to this system. And so it's going to absorb the energy, and it's going to be endothermic because it's taking energy in. It's going to be on these ones here where it's like negative, it's going to be exothermic because it's releasing energy. Energy is being removed from this system. It's exiting the system. And so that's a good way you can kind of remember that. We'll type that in here. Here, that's Gibbs. I think it's spelling that wrong. I think it's 2 B's. Yeah. Gibbs free energy. That's Gibbs free energy. Okay. Any questions there? Are we good to go? So then we're going to go and look at the laws of thermodynamics. So what is the first law of thermodynamics? It's also very, very similar to, yeah, perfect. No energy can be created or destroyed. So energy cannot be created or destroyed. The energy is just converted. So energy may be like lost from a system, but it's still, you know, going into something else. There we go. So what is the second law? So this has to do with entropy. And next step's the entropy. So entropy, if you don't remember, is like disorder or like the amount of like movement in the system. So the entropy of an isolated system or the universe is always increasing or decreasing. What do you think? Increasing. Perfect. Okay. Does anyone know what the third law is about? Oh my goodness. So the third law says that the entropy of a pure crystalline, no, I spelled that wrong. That way wrong. Of a pure crystalline substance at absolute zero is zero. So that's like literally, we'll type zero since we did that. So that's literally, so like that's literally what absolute zero means. Absolute zero is 0 Kelvin. Oops. 0 Kelvin. That looks like okay. 0 Kelvin is what absolute zero is. And that's literally what it means, is that there's no more movement of any kind. Like it just completely stops. So, does anyone know what a state function is? So it's a function with variables that only depend on the initial and final values. Do you know of anything that we talked about or that he had like in the slides or anything, or you read about, that are examples of this? I talked about these two things in our worksheet today. So one example of this is entropy, and another one is enthalpy. Because one of the ways you can solve for those is just by looking at your, oh, let's not do it actually, we'll leave that on the next page. What value of delta G signifies a reaction at equilibrium? Sorry, computer's causing me problems. So if delta G equals 0, the reaction is at equilibrium. No, and then like we talked about before, the delta G gives free energy. That's a little bigger where you can see it better. Okay. What is the regular formula for Gibbs free energy? You may know. So delta G equals what? We're talking about the one that starts with, what is this? Delta H, not, looks like the little degree symbol. I can probably put that in here. Let's see. That's not it. So this one? No. None of those are the right one. Nope. Where is it? Yeah, this one. That's it. Okay. I'm just going to copy and paste that. So, sorry about that. So, delta H naught is, key back up here. Delta H naught, and so one starts with that. If anyone remember seeing that. But delta H naught, come on. it goes, minus T, oh no, that's right, T delta S, T times delta S naught. And just like we were talking about before, we have G is the Gibbs free energy, just like we were talking about right here. The H naught here, that's our enthalpy. And delta T, or not delta T, T is our temperature in Kelvin. And then we also have delta S naught. And that is, oh, we got T. Our entropy. What are other formulas for Gibbs free energy? And we're going to talk about how they're different from each other. So one of them we have is that I'm going to go ahead and take all this. Okay. So one of them we have is that delta G is delta G naught plus RT times the natural log of Q. And if you don't remember what R is, we just talked about all those except for Q, I guess. If you don't remember what R is just a constant, and it equals 8.314 joules times moles over Kelvin. So degrees Kelvin. So that's our R value there. And another one of the equations is that whenever Q equals K, KEQ, then delta G, delta G naught. I should have left that. So delta G naught is equal to negative RT natural log of KEQ. And so if you remember, Q is the same thing as KEQ, like when we solve, except for K is at equilibrium and Q can be at any point in the reaction, regardless of whether or not it's at equilibrium. And so this is saying that whenever it's at equilibrium, which is why we can use KEQ here, we can use this equation. But because it's not at equilibrium, this is when we have to use it here. So the difference between these two is that this one can be used, this one is not at equilibrium. And this one is at equilibrium. This is at equilibrium. So there's that. And here's our last question for today. If the reaction quotient Q is greater than the equilibrium constant K, what is true about the Gibbs free energy equation? So if Q is greater than K, so it says Q is greater than KEQ, then that means that we're going to have positive G naught. So we're going to have positive G naught here, delta G naught. And that is going to mean that our reaction is spontaneous. Oh, or not spontaneous, I mean non-spontaneous. All right. So, yeah, so that's, so like it talked about the positive G is not spontaneous. Yeah. So yeah, that's what we know. Does anyone have any questions or anything like that? I didn't cover a whole lot today because I know that he hasn't done the math yet, but we'll go over that on Monday. Oh, I had another question. I'm gonna go ahead and stop recording.